P of x indexed by omega, which is exponential of I by omega, let's take D, omega x, or omega in, let's say, minus R to R. Okay, you divide by 2R plus 1 square root to have unit norm. Then you represent by having quadratic forms in P of x, you represent all trigonometric polynomials of order up to 2R. Okay, and this is what's happening. And what you could do, and in fact, this is what we do in other work with Ulysse Marteau and Alia Woody, but I won't talk about it, is we use dx omega, the q hat of omega 1/2 times the exact same thing. And now we can take all the omegas, all z. Okay, we just need the constraint of the sum of the q hat is 1. I'm not going to cover it today. The goal is to, this will apply to that, but I want to avoid like technicality. Any further questions on the general setup? Yep.
Maybe just to make it more familiar. So this case is 5x trigonometric polynomial. But you're really doing your thinking in the form of like permission PSD matrix.
Yeah.
Still this thing, right?
And then so here at the end, for that, exactly. So is it this?
So you're saying that all the extreme rays of the slide will have rank 1.
In 1D, this is true in 1D. Yeah.
In 1D, that.
Yeah, but multiply is not true. Okay, and you get closer and closer if you add more frequencies. So you embed, let's say that you take you embed, you can represent your h in a function with only like those components, but it won't be tight. You add more components, okay, so you get bigger phi, a much bigger set, okay, and then it becomes tighter and tighter. Oh, right. So a last point, which so you can rewrite this, and I'm going to use it later. Well, I know it's not the way it's typically written, but it's equivalent. So once you have that, because I have assumed that the P of x has norm 1, you can rewrite this as P of x times identity minus h, which is the quadratic form depending h, minus x times P of x 0 for all x. Okay, so this is the equivalent to that. And now the way I write it is equivalent is to say that equivalent essentially I minus h minus x is inside the orthogonal of the span of T down. Okay, so this is just, you can write this as the trace of T of x, T star of x, times I minus h minus x. And if you use as a dot product on matrices, the classical has a name which I forgot, the probability dot product. Okay, so you get the dot product in this and that. Okay, so you're saying that for all x, the dot product is 0. It means that this has to live in the orthogonal of all of the elements. Okay, so this is so then you can rewrite the sum of squares as you can rewrite this as essentially I will see as P identity minus h minus a equal to y for y in the orthogonal, okay, I call it B. Right, so I take the infimum of C or something like that. Okay, so you can, and A D increase D, so I get equivalently inch of lambda max of h plus 2 for y in the orthogonal. If you optimize over C and A being PSD, you end up C being the data value of H. What I like in this one, I like it because you get back lambda max, and I think from one of the papers you recover something about similar nature. So if y is 0, get lambda max of H, you get a traditional spectral relaxation of optimization. Okay, so here I'm using the fact that P of X as norm 1, so I optimize over all elements of norm 1, not the ones which can be written, not only the ones that can be written P of X. And the key here is that in the case of trigonometric polynomials, it's going to work. Special relaxation, if you add more and more frequencies, they end up converging. But adding the sum of squares element, which corresponds to adding the field, will make it tight very quickly. This is one way of seeing the sum of squares. Any questions on those reinterpretations? They just exactly equivalent to the first layer of the hierarchy, so they need to need it. Fine. So now let's try to see how we can add some probability. Check if I'm not forgetting something.
You have only one layer.
Yeah, it's one layer, but it includes the hierarchy for in the case of Fourier series, because in the case of Fourier series, just embed in a bigger space. There is no need to add the second set of polynomials. That's why I prefer this one. It would extend as well to the classical polynomials with the constraints. Right. So now let's do some motivation, and now I can reuse what Hamza has done yesterday. So what is the motivation? Let's take the simplest case, and I should have mentioned it, that X takes the element. Okay, and P of X is just the canonical basis vector, okay, indexed by X. Okay, so what? I'm in RB. EX is just the X element of the basis vector. So whenever I function H of X, essentially a vector of size B, okay, I can write it as P of X times H P of X. So it's a bit weird at this point. And what I put by H, I simply put, so this is what this is just sum over X of H of X. Right? And no, it is not. You can you put in H, okay, you put in H, this is for X. You put in X, essentially H1 up to HB. This is a way to represent the really pedantic way of representing like vectors in RD. Okay, and but then what is optimization then? Okay, so maximizing H of X is simply like looking at all values of H, taking the maximum. And for that, okay, so when you optimize something like this, the problem is typically this is not smooth in H. Okay, and what people do, they add some entropy regularizer to make it smooth. Okay, and my motivation originally was to do optimization. So what people often add, this is the X element, you often add something in the form minus epsilon, and you need to add a strongly convex function in H. Okay, no. Okay. You see it as max over in the simplex of sum over X, P of X, H of X. Okay. And then on this one, you add a strongly convex term, and the one I'm going to add is the entropy from yesterday. You often add something like minus epsilon sum over X of P of X log of P of X over P of X. Okay, take Q uniform distribution or anything, okay, and you add that term, which is interesting. Why? Because it's strongly convex in P. So this means that after you optimize, you get something which is smooth in H, and it's going to be easier to optimize. So this is a traditional smoothing technique. And what we saw yesterday is that this is generally convex in P and Q. Okay? And here I can do the continuation in closed form. So believe me, P star of x to be proportional to P of x times exponential of h of x over epsilon. Why? Because if you take the derivative with respect to p, you get h, you get like epsilon of p. Okay, so maybe I can do the v over v dx. You get h of x, you get epsilon log of dx over qx plus constant terms. Okay, and now P of x has to be proportional to log of Q of x has to be proportional to h of x over epsilon, and if you take exponential to get that. And at the end, you get for the max, okay, you get for the max something which is nice, which is the smooth maximum epsilon log of the integral mass sum over x, Q of x, exponential h of x over epsilon. The traditional log sum x function, which is
sorry.
yeah.
So how do you ensure that you are not on the boundary? It's simplest when you take the critical point.
There's no issue. Why P of x? Why? Oh, because the because P of p has diverging derivative at 0. So P of p, it's finite at 0. So derivatives go to infinity. So you will actually this act as a barrier function as a syntax. Right. So this is very often used for smoothing the maximum. We use a lot in optimization. Okay. But from the progressive point of view, this the interpretation is different. Okay, so this is what it is just the normalizing factor of that distribution. Okay. So when x takes d values, computing this is not a problem. Okay, but when x is going to take many values, this is going to be a problem. And the large portion of probabilistic inference is dedicated to just computing this. Okay. So just like the max, when epsilon goes to 0, the g goes away, like over the max, then you can show that when epsilon goes to 0, the log sum x will also go to the max. In other words, like a temperature limit, when the temperature goes to 0, you just put weight on the maxima of h. The traditional probabilistic Gibbs model with the h as another topic. Yeah. This review is a long method from yeah. So it's not a log barrier would be the P, but it's an entropic barrier, which is typically nice because if you were to have a log logarithm, you will get something which is also like self-concordant that will explode a bit everywhere. So it's a bit easier to do this for optimization. You get less guarantees, but right. So the goal is, can we go to take the sum of square case? Yes.
So here you suppose that small d number of points is very big.
At the moment,
otherwise, if you want to maximize h, you just evaluate h at this point. So yeah, it will be very expensive to evaluate h at that many points.
so this is a simple case where this is you don't really need to do all that. Just to show an example that when x is simple, if you add an entropy penalty, the optimizer is the exponential family here, and the final value is log sum x.
And then probably you will make it for more general capital X.
Exactly. The goal is we know that if we go from h being finitely many values to a quadratic form, we can apply SOS. Can you apply SOS to do something like that with the same benefits of having a relationship with probability? We'll try to see the way we're going to do it. And so here, let's see how we can expand to the general case. Make sure I'm not forgetting something. Nope. All right, so let's look at the general case. Now let's make x being anything, okay, and let's look at the max over h of x over x. Okay, so this is max sweep are going to be the same, okay, and so what we have done just in a moment is to see this as the max or the integral of p of x h of x, okay, for p probability measure. Okay, so this is the first this is the way of measuring max of h. And so what we will do is, like in the discrete case, we will add some term that depend on p and q. So what we would like to add? We would like to add the classical K divergence, which would be minus epsilon, the integral, okay, of log of dp over dq of x times dq of x. This is the K divergence between P and Q. Okay, so you have to assume that this is dP or dQ, the density of P with respect to Q. Okay, so this I'm loading over like the measure of probability works. And so this is the integral of extension of H minus this, and with the exact same computation from before. P star of x over dq of x will be proportional to exponential of h of x over epsilon. This is the exact same computation of everything solved by integral, and the value of this will be log of integral of exponential h of x over epsilon dq. So the question is, how can we apply the sum of squares to this? So as a note, I think Jean-Bernard, Bertima, and others have worked on a similar problem where h of x is a polynomial. I guess they use the integration by parts to access this integral. We do something we're going to relate to the sum of square on using the control entropy that Hamza has. What we study, so this is our goal. We will study a different goal. We will study the max over integral of p of x, h of x, going to change. And we will replace the distance between p and q by some divergence between sigma p and q. Let me define what is sigma p and sigma q. Sigma p is just the integral of p of x star dq of x. This is the moment of p of x transpose over p, and sigma p will be the corresponding moment over q. And what will be d? Okay, with d of a b, be the trace of a log a minus log b. Okay.
To back the distance for moment sequentiation.
So this is the name, what is the answer, you're going to create the answer, you will do essentially on that quantity, and this is for the von Neumann relative entropy. So here, this is all like spectral functions. So A is the symmetric or Hermitian matrix. The log, we take the log of the eigenvalue with the two eigenvector. Okay. And this for A and B, then the trace of A. And indeed, when A is diagonal, if A is diagonal of P and B is diagonal of Q, you recover exactly the kind of divergence in P and Q. So this is the extension to matrices.
Can you see that the distance between moment sequences?
Yeah. So we're going to, look at this. apply it to the moment matrices and see what we get. Okay, so this is I started like this. Let's add this because for optimization, this is what you would do anyway. If you want to smooth the lambda max that I had earlier, you will replace lambda max by a log sum x. This corresponds to adding this exactly. And let's see what it is. So this is so first optimization, it does what you want. So I won't give the details here, but we're going to replace. So for optimization, okay, so if you solve the problem, so if you now replace it by the trace of H sigma P. Okay, the trace of H sigma P because if H is pure vex transpose H per vex. So if you solve this, if you solve max over sigma P in my set, my approximated set minus this, then you can get that you get essentially the intimum, the group intimum over y of the log of trace of exponential epsilon and to be h plus y over epsilon. Okay, and I will put a v on that. Okay, so what is this? So you take what is the trace of the exponential, you will take all the values of that number, and you take the sum of the exponentials, you take a log, so this is a log sum x of the eigenvalues of this one. Okay, so as the log sum x with the parameter epsilon, when epsilon go to 0, you get back the maximum. Okay, so essentially when epsilon is 0 here, it's exactly the sum of squares relaxation. Okay, so you check over here the dual that I had earlier. What I had earlier was the E over Y over node of lambda max of X plus Y. Okay, and here you write over a smooth function, a smooth lambda max. So this is where, right, very classical optimization. Lambda max, you replace the lambda max by the log sum x of eigenvalues. This is convex and smooth, and then you can apply Westerhoff acceleration to this in a very classical. So this is just we work on that for optimization purposes. Okay, the goal of today is not to do optimization. The goal of today is to see if there is a link between this one and this one. Okay, because it's fine to smooth, but it's out. So let's look at the link. But are there any questions on this? Okay, one behind.
The equality on the left-hand side, the middle of the board,
Hmm?
does this include the epsilon entropy problem?
What do you mean? Here?
About
Yeah?
above the very first line,
Yeah.
so from the left, the maximum of H, is it the same as the maximum?
No, I think it means max of H of X.
No. Sorry.
You can modify going to the maximum, right? The epsilon just takes to 0.
Yeah, sorry. This is a bad board management. Okay, so I'm taking this is the max function, which I'm regularizing by the entropy, by the divergence. Okay, and if you make this disappear, you recover the max of X. Okay, and the way to make it disappear is to put epsilon being very small, and I check that the dual, if you relax it to the sum of squares, okay, the dual ends up being the same as we had before. There's a safety check. We smooth the problem. We want to make sure that when the smoothing parameter goes to 0, we recover what we had before. This is the way it is used in optimization. So to solve that, in fact, this gives you, this algorithm gives you like a 4-line algorithm to do sum of squares. Why? Because take a y, take H, y is an element of the orthogonal of V. So take V is surface matrices. We know how to project on surface matrices. So we know how to project on the orthogonal. And you can apply projective radial descent to this guy, which is easy because for every y, I do the SVD of H plus y. Okay, I take the log sum x, I take the value of this, which is just easy. Take a step, okay, project. acceleration. It's really 4 lines. I coded it. So 4 lines of code to do actually the first layer. This is not my motivation, but let's do now study if this is in fact close to that. Okay, and it will be the last element. Right, so the big question is, how can you relate D of sigma P to sigma to dpq? Right, so let's do it. And this is, I'm going to use what the highly non-trivial fact, as Hamza was saying, that this is Jonesy convex in A and B. Okay, so the fact that this is convex in A is rather simple because in A this is a linear term plus spectral function, so it's convex. So it happens to be Jonesy convex in A and B, and this is like hard to show. And Hamza gave a proof yesterday, which I won't do again. Taking that time. We're going to use convexity of D. I can write this as the divergence between the integral of P of x star dp of x. Right, this is just definition of sigma p. I can write the definition of sigma q, the integral over P of x transpose. Now I'm going to introduce the derivative of the density of q with respect to p times dp of x. Okay. Now what I have is I have a jointly convex function of a and b taken at the integral of something and the expectation of something and the expectation of something. Okay. Because I'm jointly convex in A and B, which is just I can apply Jensen's inequality, get the integral of the divergence between P of x transpose and P of x transpose d q. Remember these. Just Jensen's, okay, there's no and for this you need joint connectivity of D. Now I can look at what I have inside. This is a rank 1 matrix, okay, so with eigenvalues 0, okay, and all the eigenvalues are 0 except 1, you get 0 eigenvalue, and you get also the norm of P of x squared as an eigenvalue. Okay, so the eigenvalues of A transpose are just the norm of x squared. This one we get as eigenvalues are also 0 and P of x squared times dq over dp of x. Right. So I'm in a lucky situation where the two matrices are jointly diagonalizable. So I can simply look at the divergence between the eigenvalues. All the 0 ones will finish, okay, and I only get to take the divergence between this one and this one, and I get then equality, and because is equal to 1, then no, let's not equal to 1 yet. So this is equal to the integral. Okay, so D is like P of P. I take this times the log of this over that. Okay, so I get P of x squared and the log of the ratio, and the ratio you get dp over dq. Okay, over dq. Now I can use the fact that P of x as norm 1 or less than 1. And this is less than the integral of log and of dp over dq of x of dp of x, which is exactly the same divergence equal to d of p. So what I've shown here is that the quantity that I had here introduced totally heuristically as a way to do optimization happens to be a lower bound on dp. So the good point, then you may should wonder, okay, fine, it's lower bound, but 0 is also a lower bound, okay? So it may be a bad lower bound. So it turns out that if you let P of x be bigger and bigger, okay? So like in the hierarchies, like in the case of Fourier coefficients, you add more and more Fourier coefficients, P gets bigger and bigger, and what you can show, and this is, you can show this like in a very precise way, that this will converge to that. Okay, as you get more and more frequency, okay, you get this will converge to this. So what you get is in a very similar way as for like SOS hierarchies. You have hierarchies to get tighter and tighter approximations of this relative entropy, okay, through a simple spectral function of movements. So one consequence is that if you want to compute this, okay, and this is a classical task in many areas of data science, so more where I come from, okay, you want to compute entropies for various reasons. If you want to certify some loss of information, okay, if you add noise to the problem, you want to make sure that for privacy, for example, you want to make sure that it's not too far. There is nice work already doing this. You need to compute this if you want to test if P is close to Q. Okay, so there's many areas where you need to compute this. So what I want to finish on is going back to my log sum x. Okay, so back to my log sum x. And for the log sum x problem, essentially, since we're going to replace this by this, and we have a lower bound to get an upper bound on the log sum x. So what we're going to get directly, I'm going to get that if I take my log sum x, x1 log the integral of e of h of x x. Then, since this is equal to the integral of d of x h of x and epsilon dq, it has to be less than the same supremum over integral of d of x h of x. So we're going to use a physicist Fourier transform integral define minus epsilon d of sigma p sigma. Okay. And why is it interesting? Because now, if I have h, which is the quadratic form, so if h is q of x transpose h q of x, what I have here is a problem which is the supremum over sigma p my set case from before, the whole of all the transpose of trace of h sigma p minus epsilon distance between sigma p and sigma p. Right. And now I can do a further relaxation and replace k by k hat, which is the sum of squares relaxation. And now what I get is still an upper bound. And now this becomes the supremum over k hat, which I can access in a polynomial time, because this is just a fine hull plus FDP. This is computable, it's computable. And now I get a computable upper bound on my quantity. Okay. And as before, if I put more and more frequencies into phi, okay, if I use hierarchies, this will converge to this. So this is, and in the preprint, I have two preprints I forgot to mention. This is implemented, and you get indeed convergence. It's not fast convergence. It's not like a fast algorithm, but at least it's one which you can implement.
To conjugate with divergence.
What?
To conjugate.
Yeah. Oh, yeah. So in fact, if it's the conjugate, but so yeah. So in fact, so the way, in fact, if in k hat you have the SDP constraint, the trace constraint. This one you can directly to conjugate to get a log sum x okay, with eigenvalues. We have to account for the fact that you have the hull of the City transpose. It's a bit more complex, but we can do this in a simple. What I want to finish on for the last 2 minutes, a few extensions, just to highlight this guy. Talked about it. All right, we talked about it. Yeah.
So we got more ways of conversion of data to state.
I would say that the K and KH, so if you add more and more frequencies, the space gets bigger and bigger. So I think how K gets to KH is I don't know how to frame it, but the value when KH goes, when you get more and more, see the value for K of this problem and the value for KH will converge to each other.
So this is
Yeah, well, this is yeah, I did this for actually for the scene for the hypothesis. Yes. In fact, as a side note, when I was reading yesterday night, it may give a proof for the hierarchies, the Kelso hierarchies as well. Because when you take small epsilon, you're very close to the classical problem. So if you have a result for some x, you may have a result for the epsilon being 0. It's a traditional way in the optimization or stats as well. Regularize the problem over bound, which is easy because you can use the fact that you have like a regularizer and let the regularizer go to 0. I've not explored it, but I'm happy with that. So 2 extensions, and I stop.
Financial question on the conversion part.
Yeah.
So these problems are usually easier when epsilon is large, right? I mean,
Yeah.
optimization is much harder than.
Yeah.
So if the convergence, you see the dependence on epsilon in the convergence, that is much.
To be more precise, I have very precise convergence results for D of symmetry to DPP when the Furious goes to infinity. So this is precise because then I have a bound. We are still so but that bound depends on P and Q a bit. Okay, so it's not like a uniform bound. So to get the precise bound on this, we need a bit more work. So we have a precise bound on this one.
But so if you just so if you have the convergence of just D of sigma T sigma Q, that corresponds to actually epsilon to infinity or
no, because it's uniform, but you need some regularity of P and Q. You get try to get that what we show in fact. So D of sigma P sigma Q minus DPQ is O of sigma square, where sigma is the width of the curve of the one definition of the width of the curve. Okay? So you can show something like that, but they are for the bigos includes P and Q. So you cannot use the uniform result in P and Q, you have to do more work, which we haven't done. So 2 extensions, one, I guess 3 for Hamza and the right for others. Okay, the first is that, so in fact, this means that this was, in fact, I was told by the brother of Hamza, okay, Omar, that, all right, so among the many dependencies from quantum inversion theory, there is one which is better, which is a trace of A log the trace of log of D minus 1/2, right? D minus 1.
A to the 1/2
I A to the 1/2.
D inverse.
Okay. You told it yesterday.
Yeah.
So it's A to the 1/2.
D inverse.
Sorry. D
inverse.
And so this is always bigger, and you can show, I think essentially, as I showed it yesterday, this is also a George convex NB. So all my derivations would hold true. So because it's always bigger, then my lower bound is always tighter. Okay. So when B is identity or proportional density doesn't really matter, okay? It's just the same. But there is a nice fact, which I will not describe, is that sigma P and sigma Q, the sigma P is integral of it depends on phi, okay? So if I give you phi, okay, you may want to change phi a bit to get a better bound. Okay? The beauty of having bounds is when you have a lower bound, approximately what you want, and always maximize it, and always get better. Okay, so here it's tempting to maximize with respect to like linear changes in phi. Okay? So if you replace phi by, like say, lambda phi, you can check that in fact this one is convex, okay, this one as well. So you can do a maximize over bound, which I will not describe. You can replace this. You can replace VPQ. You can replace this by all L divergences, which are the form VQX L of VP over VQ. Okay, so when F is X log X, you recover the same one, but if you prefer Rayleigh entropies or if you prefer Pearson divergences, this can be applied as well, as long as F is operator convex. Okay, so this is only the now. And last point to conclude, let's forget. Yeah, so maybe the key equation to conclude there. Okay, so the whole take-home message is that this is doing this. Okay. Is just one version of sum of square, where K hat will be, for example, for Fourier or Paris Fourier or trigonometry polynomial surface matrices which are PSD express. Okay. This is what you will do with sum of square. For optimization, you can add only convex term to make it smooth, okay, to make it easier to optimize. This is like one point, but you can also give some interpretation of that term with regard to the true divergence. And this last point is that when you do inference in probabilities, what you care about is not the value, but the optimizer. Okay, so in fact, many tasks in a probabilistic inference is I give you a density given by potential bit distribution. I want to compute moments. Okay, and this is a traditional way in a variational inference is to solve problems like that. And you care about the sigma p, okay, in this case, a way to infer. So many things which I don't know, okay, so the exact convergence, in fact, is getting clearer. It's not totally clear yet. Efficient algorithms are not clear yet, okay, because this creates extra problems. This one, even more problems, okay, and so yeah, many potentialities, and on that, thank you for your attention.
Do we have some concluding questions? Yes.
So Q is a reference measure on the set.
Yes, simple one.
So since you need P to be absolutely continuous, you cannot expect finite convergence, right? Because you look for the hat, and P cannot be unique to the hat.
When epsilon goes to 0,
Yeah,
it does limit the
yeah. So that means that you cannot have an exact. You cannot obtain exactly the value by finite.
When epsilon is 0, no. When epsilon is not 0, yes. And so if you were to use this to prove convergence of the optimization case, you would have to see how you can approximate those types of densities, which are probably Diracs. Okay, but this is the ongoing work to try to assess if you can let the epsilon go to 0. Not obvious. Yeah.
So you mentioned that the more techniques should be used to prove the convergence of the classical
Yeah, the code is just yesterday night at 11 p.m. Oh, why not do it? Okay, so
I'm wondering there, the algebraic description of the set X is true. I'm wondering where it enters in your.
it enters in the hull in the so the relaxation. Okay, in sigma is b, square of sigma being 1, and sigma in the span, okay, the span of t of x, t of x over 3. Okay? And so this is where the properties come in. So polynomials, Henkel, and Toffler.
Could be Archimedean distribution somewhere here in your.
I think so. Here, to me, this is I don't know because I'm not very familiar with polynomials. Okay, and but
Yeah, it may be very tricky to describe the span, because capital X is complicated.
I think there is a difference here in the sense because we are used to, because as I was mentioning, the description of the set matters, but here you're just talking about the set. Like you're just talking about, taking things from your set, but algebraically, the way that your set is presented matters. That it matters which inequalities you give, it matters for the type of, how well the relaxation is. But here it's much easier to, in principle, to just work with the set itself, but that's where you're optimized.
here the span you know, okay. The hull you don't know, but the span is just topic matrices, okay. And if you have the Fourier domain, it's just like diagonals which are all equal in multi-dimensions, but the span is known for me. I guess maybe I'm wrong.
In the Fourier case, but in the semi-algebraic case, it may be very tricky.
I agree. That's why I focus on the cases for which the hierarchies are of that form. It is not the case of polynomials. It's not simply taking a bigger thing. It's more complicated, more powerful, but more complicated. Whereas here it's less powerful, but simpler algebraic.
But here X is in the VP.
X can be so the motivate can be.
So there you have a description.
You do, but okay, so you need for this to work, you need a set where the span, you know the span. Okay? You only need to access the span. Okay. And if you take, for example, Boolean Fourier coefficients, you know the span. Fourier transform, you know the span. Probably. Okay, so if you start like constraints, I don't know. So there are many things. So coming from the Fourier simplest version, so it's the first level of the hierarchy. But, if you add one layer, I don't know.
Will you stay on for the break?
I will be here.
So you can hold things within at the break after the next break. And we'll take a few minutes time to swim in the offer and move on to the next speaker.